Hi, everyone. This week, we will be beginning the topic of the semantics of our formal propositional logic. The semantics will occupy us this week as well as next week. And then after next week, we will have a review session and a midterm. So I will send an email in the next couple of days with information about this midterm. So keep an eye out for that. In any case, right now, let's jump straight into introducing the formal semantics. So in this lecture, I'm going to introduce to you the basic ideas of the semantics, and then I'm going to teach you how to construct truth tables. And constructing truth tables is really the core technique which you will have to learn in order to do the exercises for the topic of semantics. So in this video, I'm going to begin by reviewing the formal syntax of our logic, and then I will move to introducing the formal semantics. Then in the second part of this lecture, I will introduce truth tables and why they matter, and then I'll give you a method for constructing truth tables. Then in the lecture that I will upload for Wednesday in 2 days from now, I will introduce to you the definitions, the rigorous definitions of the various semantic notions which we have already seen. So for instance, validity, entailment, equivalence, and then we will then be able to begin using truth tables as we construct them to test whether sentences or collections of sentences have these semantic concepts. But today, these two videos for today will be about getting the basic ideas of semantics and truth tables out there, and then next lecture on Wednesday we will introduce the rigorous concepts, semantic concepts, and then start using truth tables to test for them. So we begin with a review of syntax. So if you recall, our logic, or what we've been calling PL or TFL, so our propositional logic has a certain vocabulary, and this vocabulary are the symbols which we build sentences out of. So first we have a bunch of basic or atomic sentence letters. So these are capital letters like A, B, and C, but also, of course, P, Q, and R, so any capital sentence letter, but then also we can put subscripts if we'd like as well. In addition to basic sentence letters, we have the connectives. We have the 5 connectives. So we have negation, conjunction, disjunction, conditional, and biconditional. Finally, we have parentheses as well. So all of these symbols here are the basic building blocks of how we build actual sentences of our formal logic. Then, given this background vocabulary, we have certain rules for how we put together parts of the vocabulary to create actual sentences of our propositional logic. So for instance, the first rule for what it means to be a sentence is that any basic sentence letter by itself, for instance, A or B or C, are themselves sentences. And then the rest of the rules tell us that we can construct complex sentences by using the connective. So for instance, if you have a sentence A, you can create its negation. And then if you have a negated sentence, not A, you can then create its negation. So you could have, for instance, not A. And you can keep on applying this rule to add negations to any sentence that you can construct using these rules. And similarly, we have recursive rules for building conjunctions, disjunctions, conditionals, and biconditionals. So hopefully this is all a review, and this is our kind of precise way of understanding what it means for something to be a sentence of our propositional logic. What it means for something to be a sentence of our propositional logic is for it to be built up by a series of steps of applying these rules, where you start with basic sentence letters, and then you construct more complex ones using the connectives. So now that we have a bit of review of the formal syntax of our language, i.e. how we understand what the possible sentences are of our logic, we can now introduce semantics. Semantics has to do with the meaning of linguistic expressions. The linguistic expressions that will concern us are just those defined by the syntax of PL. That is, the linguistic expressions that will concern us just are the sentences of our propositional logic. So anything that's built up according to these rules here. Now, the meaning of sentences for us will be truth values. And there are just two truth values. There is the true and there is the false. So any sentence of our language will have as its meaning either the true or the false. And now we can talk about the true and the false by using the capital letter T or the capital letter F. Another way you might see this done is with this T that looks like this, but then also an upside down T as opposed to an F. Or you might also see people using the word 1 for true and 0 for false. What matters here is that the meanings for us are truth values, and there are just two truth values, true and false. So every sentence of our language has one of these two things as its meaning. And of course, we talk about sentences in our natural languages as having certain meanings. And that notion of meaning is much richer than the notion of meaning in this formal model. So for instance, the sentence snow is white and the sentence grass is green, these obviously have different meanings. They say different things. However, if we are treating these as sentences of our formal language, given that both of these sentences are true, given that it's true that snow is white and it's true that grass is green, both of these sentences would be assigned the same thing as their meaning, the true. So our notion of meaning here is very coarse-grained. So we're just giving a very simple formal model of meaning, where meaning is just truth value. And it's important to recognize that this is a very simple understanding of meaning, because we can have two sentences which differ in meaning, yet which have the same truth value. So it's important to keep in mind, again, that when we're treating the meanings of our sentences as simply truth values, there's a lot of nuance and subtlety about actual meaning that we are ignoring for the purpose of simplicity. So now, our syntax, so the rules here for constructing sentences, those rules give us an infinite collection of sentences. So we can keep on applying these rules to their own outputs forever. So for instance, we can keep on adding negation signs in front of sentences. So we start with A, then we can have not A, then we can apply this rule again to get not A, then we could apply this rule again to get not A. And forever we can apply this rule to create an infinite amount of sentences where we keep on adding a negation. And similarly, that's a very simple illustration, but similarly, we can apply these rules here over and over to construct ever more complicated sentences. So given that in our formal syntax, we have an infinite collection of sentences, we need to figure out how we can assign truth values to this infinite collection of sentences. And the way we do that is as follows. First, we assign truth values to atomic sentence letters. And we do this by means of evaluation or interpretation function. So what this first step means is that we take the atomic sentence letters of our language, so for instance A, B, and C, and we're allowed to stipulate that these atomic sentence letters have a certain truth value, either the true or false. Okay, so we begin by stipulating that the basic building blocks, the basic sentence letters, are either true or false. And then given that we've assigned truth values to this atomic sentence letters, we then have rules which we can represent with truth tables for how the assignment of truth values to atomic sentences percolates up to complex sentences, given the way those complex sentences are constructed using connectives. So this is a pretty complicated idea, but in the next few slides, I will break it down to you, for you. But before I do so, let me just try to explain again at an abstract level what's happening, which is that here we have in our rules for creating sentences, we have the first rule, which says that basic sentence letters are sentences. Now, for when we start thinking about meaning, corresponding to the first rule here, we can simply assign different truth values to the sentence letters. But then these other rules here, they tell us recursively how to construct more and more complex sentences out of the sentences we already have, and ultimately out of sentence letters. And so what we need here for the semantics is a way of saying that, a rule for saying that any conjunction, no matter what the first conjunct phi is, and no matter what the second conjunct psi is, we need to give a rule for what the truth value of that whole conjunction is, given the truth value of the parts. And we can give a general rule like that, which applies no matter how complex the parts are, because ultimately we'll be able to break this down according to the other rules to looking at the truth value of the sentence letters. So let me try to explain that in a bit more detail. So here is very formally what we mean by evaluation. So evaluation function is a function v which assigns to each atomic sentence letter of the propositional language exactly one of T or F. So the evaluation function is something which assigns to each atomic sentence either truth or falsity. So we can write that as the following. For each atomic sentence alpha, either the evaluation assigns it true or the evaluation assigns it false, and never both. So each atomic sentence letter is assigned a truth value directly by evaluation. So that represents the first part here, which is that we are allowed to assign truth values to atomic sentences by means of evaluation or interpretation function. But then second, we need to have rules for how the stipulations about the truth or falsity of the sentence letters goes on to determine the truth or falsity of complex sentences, which are built up out of those sentence letters. And because those complex sentences can be infinitely complex, the rules we have to state very generally. So here we say that the valuation or the truth value assigned to a negation, a sentence of the form not phi, it's assigned true just in case the phi part is assigned false. And here we say a conjunction of the form phi and psi, no matter how complex phi and psi are, this conjunction will be assigned true just in case both phi is assigned true and psi is assigned true. For disjunction, we say a disjunction, phi or psi, is assigned true just in case either phi is assigned true or psi is assigned true. For the conditional, we say that the conditional, if phi then psi is assigned true, just in case it is not the case that phi is assigned true and psi is assigned false. So the conditional is a bit complex, and I'll return to that in a moment. But finally, for the biconditional sentence phi, if and only if psi, is assigned true, just in case both of the parts of it, phi and psi, are assigned the same value. Okay, so the important thing to note, so now I'm going to go through each of these connective meanings and give you a simpler way of stating what these mean. But what's important to notice, the one thing I want you to notice about what I have here is how it mirrors the syntactic rules here. So these syntactic rules, so for instance, for negation, it says, take any sentence whatsoever, and say that sentence is phi. So any sentence whatsoever phi, you can put a negation in front of it, and you can construct another sentence not phi. So this sentence phi could be a sentence letter, but it also could be a very complex sentence built up from the other rules. Or similarly, for a conjunction, it says, give me any two sentences whatsoever, no matter how complex they are. And then you can put them together to form another sentence, phi and psi. And similarly, these rules here say, no matter how complex this sentence phi is, the truth value that is assigned to this negation is true, or it's assigned true just in case phi itself is assigned false. So we can apply this rule no matter how complex phi is. And because phi will always be built up ultimately out of basic sentence letters and other connectives, we will ultimately be able to apply these rules to the point where we see that the truth value is dependent on the particular truth values that are assigned to the atomic sentence letters on the valuation. So again, this rule tells us no matter how complex phi is, its negation will be assigned true just in case phi is assigned false, or similarly, no matter how complex phi and psi are, the conjunction phi and psi will be assigned true just in case both phi and psi are themselves assigned true. So now let me go through these meanings for the connectives and hopefully explain in a bit more clearly what they're saying. So we begin with negation. So when I say that the valuation of not phi is true just in case the valuation of phi is false, a more intuitive way of putting that is that a sentence of the form not phi is true just in case phi is false. So again, the valuation we assign to not phi is the true just in case the valuation assigned to phi is the false. And this same fact can be represented by a truth table. So what this truth table here shows us is that if the sentence phi has a value true, then the sentence not phi will have false. But if the sentence phi has a value false, then the sentence not phi will have the value true. So this truth table shows us that when the constituent sentence phi has either of these truth values, the whole sentence will have these ones. Now, moving on to conjunction, what the fancy mathematical symbolism here just means, again, is that a sentence of the form phi and psi is true just in case phi is true and psi is true. So the valuation which we assign to the conjunction is the true, just in case each of the conjuncts is assigned true. And this same fact is represented in the following truth table. So here we have the two conjuncts, phi and psi, and then we have their conjunction, phi and psi. Now, on the left-hand side of the truth table, what we have is all the possible combinations of truth values that the conjuncts can have. So we can have that both of them are true. We can have that phi is true and psi is false. We can have that phi is false and psi is true, and we can have that both of them are false. And now, for each of these combinations of truth values of the conjuncts, the right-hand side of the truth table tells us what the truth value of the entire conjunction is in that case. So since we said that a sentence of the form phi and psi is true, just in case phi is true and psi is true, the only case in which the entire conjunction gets the value true is when both of them are true themselves. And in all of these other cases, we have at least one of them being false, so that in all of these other cases, we have that the entire conjunction gets the value false. Moving on to disjunction, the fancy thing I said above just means that a sentence of the form phi or psi is true, just in case either phi is true or psi is true. So this disjunction, phi or psi, gets true just in case at least one of the disjuncts is true. And again, we can represent this fact with the following truth table. So again, on the left-hand side, we have all the possible combinations of truth values for the two disjuncts. And then on the right-hand side, we have what the truth value of the entire disjunction is in those cases. And here we see that in these first three cases, at least one of the disjuncts is true, so the entire disjunction is true. And in the final case, we have that both of them are false, so the entire disjunction is false. Now, moving on to the conditional, and this one is a little bit more complex than the last few, so we'll spend a bit more time trying to make sense of this. But a sentence of the form if phi then psi is true, just in case it's not both the case that phi is true and psi is false. So let me say that again. A sentence if phi then psi is true, just in case it's not that phi is true and psi is false. So let me try to show you the truth value, the truth table, which represents this meaning for the conditional. In the first case, we have that both the phi and psi are true. So phi in this case is the antecedent and psi is the consequent. Okay, so in the first row of the truth table, we have both the antecedent and the consequent being true. And in this case, we have the entire conditional as true. Now, in the second case, we have the antecedent true and the consequent false. And this is exactly the case where the entire conditional is false, because we've said that a sentence of the form phi, if phi then psi is true, just when it is not the case that phi is true and psi is false. So that is to say that a conditional is false just when the consequent is true and, sorry, let me repeat that. I think I misspoke. The one and only case in which a conditional is false is when the antecedent is true and the consequent is false. So in the second row, we have the antecedent true and the consequent false. And that is the case in which the entire conditional is false. That is a case in which phi is true and psi is false. And that makes the entire claim if phi then psi false. And in all other cases, in all the rows here, which are not the row in which the antecedent is true and the consequent is false, in all those other rows, we have that the entire conditional is true. So let me try to explain in a bit more detail what is happening. So let me begin with some issues with this way of understanding the meaning of conditionals, i.e., in understanding them to be true and false in this relation to the truth or falsity of their consequent and their antecedent and consequent. So the theory of meaning which I just gave predicts that the following two conditionals are true. First, if 2 plus 2 equals 5, then humans are immortal. Second, if snow is white, then 2 plus 2 equals 4. So let's just think about this first sentence here. If 2 plus 2 equals 5, then humans are immortal. Now, this is a pretty wild thing to say, and it doesn't seem like it's true. However, if we look at our theory of conditionals, which we just gave, it actually predicts that this sentence is true. Why is that? So I want you to look at what the antecedent is and what the consequent is. So the antecedent, 2 plus 2 equals 5, is false. And the consequent, humans are immortal, is also false. Okay, so let's plug that into here. So phi is 2 plus 2 equals 5, which is false. And psi is humans are immortal, which is also false. And here, what this table says is that in this case, where both the first and the second part of the conditional are false, the overall conditional is actually still true. Because this table tells us the only case in which the conditional is false is where the first part, the antecedent, is true and the consequent false. And because the antecedent is also false, we get that the entire conditional is true. So that's why our theory tells us that this conditional here is true, even though that seems strange. Now look at this second example. If snow is white, then 2 plus 2 equals 4. Now this seems, again, like a very weird thing to say, and it seems kind of odd to say that this is a true claim. But now if we compare this sentence to our theory above, so we have phi is a sentence, snow is white, and psi is a sentence, 2 plus 2 equals 4. And those are both true sentences. So we're in the first row, and again in the first row where both the first and the second part of the conditional are true, the entire conditional is true. And that again is because, according to our theory, the only case in which the conditional is false is when the first part, the antecedent, is true, and the second part, the consequent, is false. And all other cases, the overall claim is true. And that includes both of these cases here, despite how strange they are. And despite that these are very strange things to say that are true, we're going to pretend that this is not a problem. And this arises from the simplicity of our model. So what you can do is you can just think that these claims are technically true, but they're just weird to say for other reasons. And that's how you can kind of keep our theory of meaning of the conditional as relatively plausible. Now, another problem with our theory of conditionals is that it seems to predict that the following two conditionals have the same meaning. So as background, these two conditionals are about the assassination of JFK. So what happened was that there was a man, Oswald, hiding in a building overlooking the parade which JFK was driving through, and Oswald shot JFK from his vantage point. Now, as a part of the entire conspiracy around this, many people think that there was a second shooter hiding behind a grassy knoll in front of the car down the street. So now, given that background, I want you to consider the following two conditionals. First, if Oswald didn't shoot Kennedy, then someone else did. Now, this claim, upon some reflection, is one that should be accepted by anybody, regardless of whether you are a conspiracy theorist or not, because JFK was, in fact, shot by someone. Someone did shoot Kennedy, and that is something that everyone accepts. So given that Kennedy was, in fact, shot, if Oswald didn't shoot Kennedy, then someone else did. Okay. So, of course, most people who aren't conspiracy theorists think that Oswald did shoot Kennedy. But still, if you think that Kennedy was shot, which he was, it's true that if Oswald didn't shoot him, then someone else did. And that is true or should be accepted as true by anyone, regardless of whether they believe in the conspiracy that there was a second shooter behind a hill down the street. But now, in contrast, consider this other conditional. If Oswald hadn't shot Kennedy, then someone else would have. Now, this sentence is one which is only accepted by people who believe in the conspiracy theory that there was another shooter. Because if you think there was another shooter, then you think that if Oswald hadn't pulled the trigger himself, then this other person, the other shooter, still would have shot Kennedy. But if you do not believe the conspiracy theory, you'd think that if Oswald hadn't shot Kennedy, then no one else would have. Kennedy wouldn't have been shot. So it's possible to imagine that these two conditionals differ in truth value. So it can be true that if Oswald didn't shoot Kennedy, then someone did, but it can be false, still in that case be false, that if Oswald hadn't shot Kennedy, then someone else would have. So what that means is that these two conditionals seem to differ in meaning. However, we only have, in our theory, a single meaning for the conditional. So our theory cannot explain the difference between these two conditionals. And now the difference between these two is a complex topic, which we'll not go into in this course, but in short, this first conditional is what is called an indicative conditional, and the second one is called a subjunctive or counterfactual conditional. And simply put, the tools we have here in our truth functional logic simply do not give us the power to make sense of this distinction. So I'm just going to note it, but then as a problem, but then move on to just simply developing our simple theory. Okay, so I want to conclude this video. I want to say a few words in defense of, or trying to explain why we have this very strange truth table as the meaning of the conditional, despite these obvious problems with it. So as we will see, when we develop the tools of how to construct truth tables for arbitrary sentences, and using that method of constructing truth tables to test for semantic notions, what we will see is that this meaning that we've given for the conditional results in the following. An argument with premise 1, the conditional if phi then psi, and premise 2, the claim phi, to the conclusion that psi, we will see that that is a valid argument. And this is good because this is, as we've already seen, the argument for modus ponens. So this meaning for the conditional makes modus ponens valid, which is good. We will also see that the following is not a valid form. Premise 1, if phi then psi, premise 2, psi, therefore conclusion phi. Now this is a form of affirming the consequent, and we saw that this is not a good argument form, and our meaning for the conditional also will explain how this is not valid. Furthermore, we want any sentence of the form if phi then phi, so the idea that phi leads to its own truth, that seems to be a clearly true claim. We'll see that any sentence of the form if phi then psi is a logical truth. And as it turns out, the meaning we've given here for the conditional is really the only meaning we can give, given our constraints, that makes all these things happen. And that is what is good about the meaning we have given for the conditional. So now so there's one more thing, which is that how the biconditional works. So a sentence of the form phi if and only if psi is true just in case phi and psi have the same truth value. So that corresponds to our fancy mathematical statement from earlier, which is that the valuation of the biconditional phi if and only if psi is true equals true just in case the valuation of phi equals the valuation of psi. And again, we can represent the same fact in the following truth table. So in the cases in which both phi and psi are true, the entire biconditional is true. In the case in which both phi and psi are false, the entire biconditional is true. And in the other cases, phi and psi have different truth values, so the overall biconditional is false. So in the next video, I will explain to you what truth tables are, why they matter, and how to construct them.